Okay, so this is our second lesson on linear approximation here, and notice, read the problem here. My example looks just like our examples in the last problem, right? Essentially what we're doing is we're taking a derivative of this function. I guess that's the new step. You have to take the derivative yourself, but you guys are already good at that. And we're using that derivative to estimate where f is at a certain point. Okay? So take a derivative at x equals -1, and then estimate using that derivative what f is at -5. The step we're adding is we're going to consider the second derivative here. And the second derivative is going to tell us something specific about our guess, right? So our guess can be either an underestimate or an overestimate, right? So we can either be wrong because we guessed too high or guessed too low. I'm going to draw a couple of graphs here to introduce this idea, and then we'll come back to our example. Okay, so the connection to the second derivative is actually pretty intuitive. Okay, so notice I have two functions, right? Both are increasing, so both have derivatives greater than 0, so f prime is positive and g prime is positive. But f is concave up, g is concave down. So f double prime is going to be positive, so my derivative is increasing. G double prime is going to be negative because my derivative is flattening out. Okay? Let's draw in some tangent lines. So let's say I'm estimating f using a linear approximation at this point. Notice any point that I pick, my tangent line is lower than the actual function. So this tells me my estimate would be an under approximation. Because the value I'm guessing on the tangent line is below the value of the actual function, right? So you can memorize that, like, when the function's concave up, a linear approximation is always an under approximation, or you can sketch the graph and think it through. I prefer the latter. Same thing here with my function g. If I draw a tangent line, notice any estimation that I make, say at this particular x, always going to be an over approximation. Out of space there, but over approximation. So the linear approximation, the estimate, is above the actual curve of g. Right? So you can also memorize that when g is concave down, the second derivative is negative. You always get an over approximation using linear approximations. Or again, you can just think it through. So let's return to our example now, and we'll see what this looks like in practice. Okay, so f is the function 3x to the 1/5 power. We have the approximation of f of -0.85 at x equals negative. So let's see what this looks like. The first thing I'm going to do is I'm going to take my derivative. So f prime of x is going to be power rule, right? So 3/5 x to the -4/5. F double prime of x is going to be power rule again, -12 over 25, so I've multiplied my fractions there, x to the -9/5 now. And it's fine for this to leave it as negative exponents. Often, like Delta Math would want you to put into sort of more proper form using roots and positive exponents, but it's fine. Okay. Now, we are going to find first our tangent line. So my tangent line, remember, I need a slope. So we're going to find a tangent line. My slope of my tangent line is going to be f prime of, well, our tangent line is at x equals -1, so we're going to do f prime of -1. Okay? So I'm going to plug that in. And you can do this on your calculator. Make sure you put the exponent in parentheses. You're going to get 3/5 for your slope. And then the equation of my tangent line, right? Well, it's going to be y minus y1 equals 3/5 x minus x1. And we know that our x1 is -1, so x plus 1. And then we need my y1, right? So y1 is going to be f of 1. I'm going to plug that in. And looks like f of 1 is going to be 3. So my tangent line is going to be y minus 3 equals 3/5 plus 1. And then delta math wants y isolated. Notice it says y equals. So I'm going to rewrite it that way. I'm going to say y equals 3/5 x plus 1. You can write it, like rewrite it all the way to slope-intercept form, but you don't need to, I don't think. So there's my tangent line at x equals 1. Okay. My approximation, I'm going to plug in that -0.85. Okay. So that's going to look like y equals 3/5. So this is my approximation now. Y equals 3/5 times 85. 85 it is, plus 1 plus 3. Again, you can put your calculator and you should get y equals -2.91. Okay, so we'd say f of -0.5 is approximately -2. Okay. So we did all of that in the last lesson. So make sure you pause and reflect on whether you followed that or not. You should be good at it by now, though. All right, moving right along here. So we are looking at this point x equals -0.85, right? So this is x is less than 0. So we say when x is less than 0, so x is less than 0, f double prime is, so our options are positive or negative here. And notice here, if I put in a negative number, any negative number, I'm going to get a positive result. And you can check that on your calculator. So this f double prime is positive. Okay, so meaning f is concave up. And our value, -2.91, is an under approximation, based on the logic that I showed you when I drew those graphs earlier. Okay, so this is, just to be clear, this is like the very end of the delta math. This is what you put at the bottom of the gray box. Okay, so the sign you pick for x goes with the point that you're estimating, right? So I picked x less than 0 because my x is negative. Then you can plug in this x or any x that's negative into the second derivative, determine whether the function is concave up or concave down, and then that tells you whether it's an over or an under approximation.